Swayam Prabha. Digital India. Educated India.
So we will look at more matrix operations in R. So we'll first start with concatenating matrices. Matrix concatenation refers to either merging rows or columns to a matrix. If you already have a matrix and you want to increase the number of rows of the matrix with specific rows, you could use the command rbind. If you want to increase the number of columns in a matrix using some specific columns, you can use the command cbind. The key thing to remember here is when you have these matrices and when you are R binding or C binding rows or columns, one has to ensure that the consistency of the dimensions are the same. So for example, if you have a 3 by 3 matrix and you want to R bind a 4th row, you cannot have more than 3 elements in that row. If it's more than 3 elements in the row, it will be inconsistent. And as we will see this in the next slide when we see an example. So let's take a matrix A, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. The other matrix is B, 10, 11, 12. If you wanted to put the row of B, 10, 11, 12, below the first 3 rows of A, you could use the command C is rbind A, comma B, which basically gives you 1, 2, 3, 4, 5, 6, 7, 8, 9, and the last row that we took from B, which is 10, 11, 12. So you got a matrix now which has 4 rows and 3 columns. You can do a similar bind in terms of columns. Now notice the A matrix is the same, but in the last slide, while B was a row vector, in this case B is a column vector, so you can actually use cbind to add the B's column onto A. So if you use this command C is cbind A, comma B, then you get this composite matrix which has the first 3 columns from A and the last column from B. So you got a matrix which is of size 3 by 4. Now a simple question for you. If we were to take this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9 and another matrix 10, 11, 12, can you cbind these 2 matrices? Would the dimensions be consistent is something that you can check with R. So there are, as I mentioned before, you can either cbind using A and B, or you can also use a command which basically places this matrix next to each other. C is A, give space B. There are other operations that you can do with matrices, some of which we had seen in the previous module. We'll go through this again, reinforce these ideas, and we have seen many of these ideas also previously in lists and data frames. So the syntax is very similar to what we have seen before. We had already seen this. If you want to delete a specific column, you take a matrix and then say nothing, comma, -2. Basically, you're telling R that keep the matrix with everything other than column 2. Now, if you assign that back to A, then the A would have changed and you would get a new A without the second column. Similarly, if you want to get only the first and third rows of matrix A, you can assign A to A with the second row deleted using the syntax, which is -2, comma, space, and it will only fetch the first and third rows. Now there are cases where you want to predefine certain matrices. We had already seen this before when we predefined a constant matrix with only numbers 3, or we predefined a matrix only with diagonal elements. There are more sophisticated things that you could do. For example, if you wanted a matrix with only random entries, you could use any kind of distribution to do this. Here there is one example that I am showing here, which is matrix, fill the matrix with some distribution, and the distribution has certain parameters. You specify the parameters, and as we saw before, n row and n column tells you the number of rows and columns that should be there in your matrix. So for example, if you take matrix R norm 9, mean 0, SD equal to 1, n row equal to 3, n column equal to 3. That's normal distribution. The arguments within the bracket gives you the parameters of the normal distribution, and what you're asking for is a 3 by 3 matrix to be filled up with random numbers from this distribution with these parameters. Now you could change the distribution. In the next case there is R uniform, or binomial for binomial distribution, or exponential distribution, or exponential, and so on. So the syntax is the same, whatever be the distribution. You have to mention the type of distribution, the parameters that go into defining the distribution, and the number of rows and columns that you need the matrix to be. Now that we have seen how to construct matrices, diagonal, random, and so on, we have also seen how to access different rows and columns and subsections of matrices. We will look at very simple arithmetic operations with matrices, which are very similar to arithmetic operations with numbers, with some differences which we will see as we go along. So we are interested in addition, subtraction, multiplication, other matrix operations, and matrix division. We'll point out some important differences between how matrix division is done in other programs and in R. Supposing you have two matrices A and B. If you want to add these two matrices, you simply use the command A plus B. You have to keep in mind that this A and B have to be dimensionally consistent for you to be able to do this addition. Similarly, if you wanted to subtract matrix B from A, you use the command A minus B, and again keep in mind that these matrices have to be of consistent dimension for you to be able to do this. Now, when you want to multiply two matrices, in standard linear algebra, we simply write A times B. And if we were to do the same thing in R, and then say the multiplication operator is star, so let me do A star B, what R does is not the standard matrix multiplication that we think about. What R does is an element by element multiplication. So if you take this example of A star B, you see the result, which is 3, 2, 9. The way that the first row of the result, the way that comes about is it does an element by element multiplication. If you take the first element, which is 3, it's going to be the first element of A multiplied by first element of B, 1 times 3. If you take the second element, which is 2, it is going to be the second element in the first row of A multiplied by the second element in the first row of B. And similarly, the last number 9 is 3 by 3. So this is not your traditional matrix multiplication. This is element-wise matrix multiplication. Now keep in mind, when you do data analytic algorithms, both the regular matrix multiplication and this element-wise multiplication are both very useful. So this is a useful multiplication, but you just have to keep in mind when you write your code that this is not your standard matrix multiplication that you do. If you want to do a standard regular matrix multiplication, all you need to do is put percentage sign before and after the star. So which is what is shown there. A percentage star percentage B would give you the regular matrix multiplication that one would look for. And accessing, editing, deleting things in matrices, we have seen enough of this. It follows pretty much the same ideas that we have used in lists, data frames, and in matrices before. You can always remember when you do operations with a matrix, the first element within the square bracket stands for row, and the second element within the square bracket stands for a column. So for example, if you take A, comma 1 colon 2, that basically means since I give you no information about rows, you have to take all the rows, but I've given you information about columns. Just pick 1 and 2 columns and so on. So this is very, very similar to what we have seen before and repeated several times before. Another interesting aspect of matrix division, similar to a multiplication, is you cannot get an inverse by doing a division. So if I say A divided by B, if you take these matrices 4, 9, 16, 25, 2, 3, 4, 5. So A divided by B gives you 2, 4, 3, 5. So this is really not your standard inverse. So division is not inverse. It is doing this element-wise division in this example.